All right, hello everyone, and welcome to today's seminar. Today I'm happy to have Dr. Ian Mann with us. Ian received his PhD from the University of St. Andrews, modeling ULF waves. He continued his work and research on ULF waves as a postdoc at the University of Alberta before accepting a faculty position at the University of York back in the UK. In 2003, he accepted a position at the U of A and returned as a faculty member, holding a Canadian research chair in space physics. Ian is currently the PI of the Charisma ground-based magnetometer array and the PI of Radicals, the radiation impacts on climate and atmospheric loss satellite, which he is here to discuss with us today. Ian, if you'd like to take it away.
Thank you, Kyle. Hopefully you can hear me just fine. So thank you for the invitation, Kyle, and for the opportunity to present on radicals. So my goal today is to provide an overview of the opportunity presented by radicals and to encourage all of you, perhaps colleagues even that you have who are not able to join this call to come together and to think about how best to exploit the data from this upcoming project. So the first thing I really want to do is thank all of the science team members and the instrument team and the mission team members who've contributed to this project. You can't do a mission on your own, and so this is really the efforts, and it'll be the ongoing efforts of a large number of people. So this is a Canadian mission. It's funded by Canada Foundation for Innovation with partner funding from the Government of Alberta and from the Canadian Space Agency. And this has enabled the Canadian team, now also joined by University of Colorado Boulder, to put together essentially a Canadian contribution to understanding the solar terrestrial connection and focusing in particular on trying to understand the physical processes and the consequences of radiation, energetic particle radiation that's scattered down into the atmosphere. And my goal today is to really explain to you about the Radicals project, where we are, where we're going, and what we hope to achieve. So it's a low Earth orbit mission, focusing on the characterization of radiation, resolution of the pitch angle of particles, as well as the populations of trapped and quasi-trapped radiation that you see from this altitude. It'll be going into polar sun-synchronous orbit, and from there we'll make measurements of this radiation, as well as some of the magnetic plasma waves, and image the X-rays that come back as a result of that precipitation. So we're trying to understand an element, a specific element of the coupled geospace system, but with a view to trying to understand the precipitation of radiation into the atmosphere, to think about middle atmosphere, and indeed coupling that might go down all the way to the troposphere. So we think this is an interesting and focused voyage of discovery in this system, focusing on a specific element of the dynamics and trying to understand it both physically and in terms of its impact. So just a little piece of history where we started from and where we're hoping to end up. I will say out of the gate, this is a fully funded mission. So we're in the very pleasant state that we have all of the money allocated for the project, all the way through mission phases, through into launch early operations, and then after commissioning operations on orbit. So there's a bit of a long history with this mission development. It started in 2016, and then funding was eventually allocated from CFI in 2020. We secured matching funding from the Government of Alberta and Canadian Space Agency in the years thereafter, and then we initiated the project with first spend around April of 2022. So the trajectory of the project seeks a launch, well, as early as we can, but realistically that looks like it'll be Q4 2026 or Q1 2027. So we have a heritage payload, a heritage bus, and we're focusing in particular on this precipitation and the climate pathway, and quoting specifically from, I guess, the most recent, but not the shortly to be released, I guess, heliophysics roadmap here, trying to target the precipitation and maybe thinking about the impacts that there might be through the NOx and HOX pathways from the catalytic destruction of ozone in the atmosphere, and then consequences in the middle atmosphere and below. So just a quick mention about the solar cycle. We're kind of racing the solar cycle, I suppose. We know recent solar cycles compared to historic have been at least smaller in terms of the overall sunspot number. But even with the, excuse me, the recent updates to the predictions, For example, this is showing NOAA's latest update of the solar cycle. We look like we'll be launching sometime in the early declining phase and be able to make measurements through the declining phase and down towards solar minimum. Just as a comment, our baseline mission is a 2-year mission, but we have funding in place for operations, at least from the ground station and so on, for at least another 3 years, subject to ongoing spacecraft and instrument health. So we're anticipating 5 years of operations constituted by this 2-year prime, and then what we hope will be a straightforward transition into 3 years of extended phase. So I want to emphasize that this is a science mission. So we do want to go after the fundamental processes that are involved with the scattering of radiation into the atmosphere. And I'll repeat what a number of people have heard me say in the past, that I still think this is a fantastically interesting fundamental plasma physics laboratory that we can visit in situ. And that gives us a major advantage in trying to actually reach science closure on some of these questions. And that philosophy is emphasized in the mission design that I'll explain a little bit as we go forward during the seminar. So this is an element of solar terrestrial coupling, of course, a particle coupling from the ionized to the neutral atmosphere. I think that boundary has been historically somewhat ignored, if not largely ignored. It's scientifically challenging, but this energetic precipitation pathway provides an avenue for us to start to understand the coupling between space weather and terrestrial weather, or at least terrestrial climate, between the ionized and the neutral atmosphere. So, I mean, we all know that this is the case. Space is vast, and so the challenge to understand solar terrestrial coupling is great. So even with a NASA Heliophysics Great Observatory and other international contributions, we're largely undersampling this region. But what we want to do with this mission is to fill in the kind of the pathway that the energetic particles will go through as they enter the atmosphere, and to understand the strength of that coupling as the particles barrel down into the neutral atmosphere. Now, even then, if you think about atmospheric coupling, and this is a Grabowski figure, the courtesy of NASA, and I really like it because it indicates the complexity even of kind of magnetosphere, ionosphere coupling, and then into the middle atmosphere below. And we're focusing on just one element of this energetic particle precipitation pathway. I'll explain a little bit more about that later. So I hope you can see this movie here. What we're envisaging is to try to take a view of energetic particle dynamics. For example, here's an electron drifting and bouncing around in the presence of some plasma waves, perhaps the large-scale ULF waves or higher frequency plasma waves. Maybe that causes an increase in that trapped radiation population under certain forcing. And then at other times, that radiation is dumped down into the atmosphere through a variety of scattering processes. And so we'll be monitoring that scattering process at the low Earth orbit end of the field line, where the loss cone is expanded and large, for us to try to understand how particles end up in the loss cone, with what strength. Is this a nonlinear, linear interaction? What are the characteristics of loss cone filling? And ultimately then, how much radiation makes its way down into the atmosphere under different conditions of forcing? So I think it's fair to say that the NASA Van Allen probes have represented a really very significant step forward in our understanding of a lot of the, especially acceleration processes. But the problem, of course, from missions in the equatorial plane is that the loss cone is very small, a few degrees or so. Whereas if you make measurements of this from low Earth orbit, the loss cone opens up to maybe 60 degrees or so. So now we have the opportunity to start to look from low Earth orbit at the characteristics inside the loss cone. And that's what we'd like to do, not just to look inside the loss cone, but also to resolve the dynamics of the trapped, quasi-trapped, and as well as the precipitating populations, all the way through the loss cone, from the edges of the loss cone right into the heart of the distribution near 0 degrees pitch angle. So that's what we're going to do. Radicals is a microsat, so it's a very focused vehicle, quite a small vehicle, but with a focused payload. So we have an energetic particle suite looking at the electrons and protons that come past the vehicle as it follows its orbit, magnetic measurements of plasma waves, and then also X-ray imaging to see the distribution, the spatial distribution of X-rays that are produced by Bremsstrahlung precipitation in the vicinity of the vehicle. And this small but focused payload gives us an opportunity really to probe the characteristics of these dynamics in unprecedented detail. Now, I couldn't really give a talk like this without trying to emphasize the complementary measurements that are available, especially in the Northern Hemisphere in Canada, but also around the world to complement these measurements from radicals. So here you're seeing just the Charisma magnetometer array, but Canada has an extensive set of instrumentation to measure precipitation from rheometers, flows of superdome radars, auroral imaging, and so on, in a two-dimensional continent scale. And so we plan to leverage ground conjunctions with this mission as much as we possibly can. Clearly with Canadian infrastructure, but we're also very interested in partnering with other ground arrays from around the world and doing something similar on a more global scale. So I encourage you to reach out to us and to think how we can work together towards that science. So just to focus in a little bit on the specific pathway, I mean, there are a number of theories that have been advanced to suggest how space radiation might influence climate. And I guess one of the favored ones is this energetic particle precipitation pathway. So this is a schematic that's put together by William Ward that builds on the work of a number of other people. And so the basic idea is that energetic particle precipitation can make its way into the atmosphere. Depending on the precipitation energy and the species, the particles reach to different depths into the atmosphere as they deposit their energy. And they can change some of the characteristics there. In particular, ozone dynamics are thought to be important and are shown in models, at least, to have a strong influence in middle atmosphere dynamics that do reach all the way down to the troposphere. I think in terms of proton precipitation, this effect is quite well known in models and well demonstrated. In terms of electron precipitation, where events might be more frequent, but perhaps at a smaller magnitude, the integrative effect of those particles is, I would say, less well understood. And in order to make advances, what we need is to understand how many particles are coming in, essentially so we can establish kind of how big is this knob, how much does it get twiddled in terms of how much radiation makes its way into the atmosphere. And then the coupled atmospheric models can examine the consequences of that in a systematic and well-constrained way. So just to expand on this a little bit, there are, I guess, two competing pathways that think about how this might manifest itself. So one is so-called direct effect. So particles of enough energy can make their way into the middle atmosphere and to have an impact, for example, on the NOx and HOX populations there directly. So this diagram that you see on the top right, adapted from Baker et al. 2012, shows different species and different energy populations, the ionization rate that's created by those populations as a function of altitude. So you can see, for example, solar protons make it down significantly into the atmosphere, radiation belt electrons less so, and then, for example, lower energy auroral particles are higher up. So the so-called direct pathway looks at radiation belt energies, maybe hundreds of keV up to MeV, making their way down into the middle atmosphere and directly affecting the NOx and HOX populations without requiring any atmospheric transport. However, lower energy particles that impact higher up in the atmosphere may also have an impact there, because the atmospheric models show that they could be transported to lower altitudes. Their lifetimes are sufficient that they can still affect the middle atmosphere ozone in an indirect way. So this is a two-step pathway: precipitation into higher altitudes, and then their transport into the region of effect in the middle atmosphere as a secondary element. And it's still not really understood whether either or both of those have a significant contribution to make. And our goal here is to make a contribution to understanding that by taking the appropriate measurements and then constraining the process. So that's what we're going to do with this project. This is the same slide as I showed earlier, trying to couple in on this issue of space weather and climatic coupling, and to focus on this particular pathway that's poorly constrained. So I will emphasize that this is a very strong Canadian collaboration, although now that the mission is funded, we're excited to bring in international collaboration as well. And won't be talking too much about that here, but there's an opportunity perhaps to combine with other missions, either that will be operating or that are proposed, to try to think about creating some kind of a mini constellation of measurements that might operate at the same time. For example, the IMPACTS mission is funded and it will operate with an overlapping period to this. And there may be other opportunities in the international community to start to bring together a constellation approach to this particular problem. So I guess one thing I do want to emphasize here is an advantage that we have. The government of Canada have generously offered us, on a best efforts basis, access to very large dishes on the ground. So this provides S-band communications from our vehicle with a large data throughput. So we expect to be able to collect data and operate continuously throughout the lifetime of the mission and through every orbit, combining both continuous survey as well as high resolution time domain burst modes. So this is quite a significant opportunity for us, because it means not only can we collect data on orbit continuously, but also we'll be able to get it to the ground. So here's our kind of overall mission goal. We really want to establish the physical processes responsible for the loss of space radiation into the atmosphere, characterize how much that is, and then ultimately through partnerships with modeling and other programs, determine what the impact might be ultimately on climate as a result of that precipitation. So I'm going to spend the rest of this presentation talking a little bit more about the payload, just to give you a better idea of the scope of the measurements that should be available. So the payload comprises 4 instruments, all of which have heritage. They've been funded extensively by Canadian Space Agency through instrument development programs, for which the team is extremely grateful. And it's nice to have an opportunity then to take this instrument development into a flight pathway and to see the payload instruments flown in a coordinated way as part of an integrated science payload. So as I've mentioned, we're interested in high energy particles. So there's a suite of 3 instruments called the High Energy Particle Suite. I'll explain the nature of those 3 instruments. Essentially, there's a low energy, a high energy telescopic measurement, complemented by a much higher temporal resolution measurement focusing on microbursts. There are 2 magnetometer payloads, one comprising dual fluxgate magnetometers, and then anteposed on another boom, a search core magnetometer, and then an X-ray instrument payload, which itself also comprises 2 instruments, one focusing on spectral information and one on more spatial information. And so the principal leads, the instrument leads for these is Professor Fedoseyevs from the University of Alberta in the Department of Electrical and Computer Engineering, David Milling from Physics at the University of Alberta, and then Professor Chris Cully and his team from the University of Calgary. So the payloads will be integrated into this platform. I mentioned earlier, the idea is that we would measure the precipitation of particles. And a key element of the mission design is that the spacecraft is going to be put into a Thomson spin. So think about a cartwheeling gymnast that cartwheels along the direction of the spacecraft's orbit in its high inclination polar orbit. And so there's a spinning configuration that's stable. So telescopic particle instruments that you can see in this diagram here will sweep through different angles with the background magnetic field, and therefore, and they're back to back. So once every half spin, we'll produce a pitch angle distribution of energetic electrons and protons. You see the boom-mounted magnetometer payloads. The fluxgate payload is 2 payloads, 2 instruments separated at different distances along the boom to try to remove spacecraft noise from the ambient geospace fluctuations, and then a search core magnetometer on a boom that's at the opposite side of the spacecraft to that. And then finally, X-ray imaging, again from 2 sensors as part of the X-ray imaging package. And all of this, as mentioned earlier, is focused on trying to establish the causality of plasma wave interactions with particles, precipitation into the atmosphere, and to really understand the energy budget associated with this process. So I mentioned that the spinning. So the spacecraft is in the stable Thomson spin, polar synchronous orbit. And the issue that we will have here is that the spacecraft spin provides you with a pitch angle distribution, but obviously this couples temporal and spatial information. So as the vehicle travels along its orbit at 7.8 kilometers a second or so, then as the spacecraft spins, we'll build up a pitch angle distribution, but by necessity, at least the telescopic measurements will come from different L shells as a function of time. So we'll build up these pitch angle distributions that do combine spatial and temporal information. The nominal spacecraft spin is quite slow, 30 seconds, and that's designed so that we'll be able to get good signal to noise of the relativistic particles for the geometric factors that are available for the scale of the instruments on this vehicle. And we have the capability to change the spin rate, so we anticipate we might go as high as 10 seconds, but faster than that, we're worried about starting to saturate the magnetometers or to start to kind of have spacecraft spin that starts to wander into the EMIC frequency range, which we want to avoid. I'll explain a little bit more. We also have two back-to-back 2-pi steradian measurements available to us from a scintillator instrument looking at microbursts, and I'll explain how that instrument is to be set up a little bit later. So here's kind of a slide showing really the most important element of this innovative design. And the idea is through the spin to be able to fill in with at least 10-degree resolution the pitch angle distributions. So if you look in the plot in the top right, it's showing kind of a schematic representation of the lost cone in low Earth orbit as a function of pitch angle, as a function of some normalized flux. So under quiet conditions, perhaps there's a reduction of the flux towards the lost cone from the locally mirroring population at 90 degrees that leaves the lost cone empty, or maybe only slight trickles into the lost cone. But then as activity builds up, then transport in the lost cone might be more active, and we may start to see pitch angle distributions that are partly filled in. And maybe under very strong coupling conditions, you might see an almost completely filled lost cone. And being able to distinguish between these different states at different times and under different forcing requires us to have a pitch angle resolution. And that's really the goal of the mission overall. The new piece of information we'll have here is to fill in this pitch angle distribution. Now, you could compare, for example, what this measurement will be like compared to what's available from fixed look direction detectors. So in the bottom left, you see an attempt to at least schematically compare what might be available from the 0 and 90-degree detectors from POSE, where you're seeing kind of an integrative effect over their overall angular field of view. And so we'll be taking a step forward compared to POSE, for example, to be able to fill into the lost cone. To give due deference to Elfin, I think the Elfin measurements have shown us very interesting results about the dynamics of the pitch angle distributions inside the lost cone, and almost validates the mission design that we have here to demonstrate that these measurements are really important for understanding how much energy makes its way into the atmosphere at different times. And so we will go after a resolution of that for 5 years, once every half spin from this detector payload. So what advantages do we have from this mission, maybe as compared to Elfin and to other missions that have flown before? So the pitch angle resolution comes from a back-to-back energetic particle detector in a telescopic form, measuring back-to-back distributions. So down and upgoing measurements, for example, inside the downgoing and upgoing lost cone at the same time, as well as magnetic measurements of plasma waves. So we'll have pitch angle coverage from spin. If we wish to set the spacecraft into a 3-axis stable mode, for example, for X-ray imaging, we have the capability to do that. And we look at special mode operations, perhaps in conjunction with ground operations, to use that mode on a campaign basis. The XRI measurements will give us spectral information of the photons as seen from this orbital altitude, as well as a spatial distribution. And the data link that I mentioned earlier is sufficient that we'll be able to do this on a continuous basis. So this is a really nice opportunity. So let me spend the rest of the time here perhaps talking a little bit about the instruments. Some of you may be wondering about energy ranges and some elements around that. So I'm going to give you kind of a high-level overview of the payload as it stands. I would say that we're at the stage now where the instrument designs are getting somewhat mature, and encourage those of you that are interested in these measurements to talk to us. We've reached out to a number of people that are active in the science in this domain already to try to make sure that the way we design the mission brings maximal science. And for that, we need to make sure we're making the measurements that perhaps some of you may need in order to advance your own scientific interests in the course of the project. So let me start with the Radicals high energy particle suite. As I mentioned, it's actually 3 instruments that comprise this suite. So there's a low energy head, a high energy head, and then the microburst detector. So these are the low energy and high energy head have different cross-sectional area segments. They're a DEDX design with different geometric factors to focus on different energy ranges. So you see the approximate energy ranges here between LE and HE, from around 100 keV up to half an MeV, and then from half an MeV up to about 4 MeV for electrons, and then protons in the 1 to 5 or so MeV range in LE, and then up to several tens of MeV in HE. We're still looking at the number of channels and so on, but we're targeting 10-degree rotation resolution, approximately half-second cadence, and delta E over E inside 30 degrees. And we're looking at how many channels we want to try to specify from the instrument performance now. And I'll show you some examples of that in a few minutes. So during the later phases of mission design, we also realized that the microburst process, where there may be an intense burst of precipitation on short time scales, perhaps 100 millisecond time scales, could be a really important element of the precipitation that's measured over longer time scales with the telescopes. So being able to monitor the temporal variation would be a very valuable addition in order to disentangling the causality of various scientific and physical processes that might be going on. So we've added a microburst detector, and it's 2 pi essentially half omnidirectional measurements with a 10 millisecond cadence, where we look at high temporal variation of the particles. And because of this large omni field of view, the combination of these 2 half detectors in various ways will allow us to see bursts of particles that are coming down, for example, in the downgoing loss cone as a result of microburst interactions. So this detector is designed to capture some of the energy dispersion at the right temporal cadence of those bursts, focusing on the capability to go to relativistic energies where there are some important unresolved problems. This is a burst-based detector because at that resolution we'll have a lot of data, and so the instrument will run continuously, but we'll use burst algorithms to store the information of relevance. So here's a representation of the design of the 2 low energy and high energy heads. So there are 2 low energy heads that view back-to-back separately, and then the high energy head has an integrative common axis back-to-back viewing geometry where particles coming from the left and from the right are detected and resolved in the same stack. And the energy deposition in the different elements of the silicon wafers in the stack gives us the ability not just to separate energy, but also species and the direction of arrival through the telescope. Strongly shielded from the sides to focus on, how can I say, clean, along axis measurements with high species and energy resolution. And I'll show you some kind of examples that come from Géant 4 simulations of the instrument performance. You'll see there's quite a large number of elements in the stack for HE, but only 3 for LE. So LE works in a more bolometric way, I suppose, where we're counting the energy that comes into those 3 elements and using that as a way to separate the energies. The lowest energies are then blocked from both LE and HE with material that covers the front of the detector. So, for example, this is a GM4 simulation of the energy deposition into the 3 elements in the LE stack, and then an example set of channel efficiencies comprised by differencing and gradienting of the measurements from the energy deposition profile. And we're looking right now then at trying to increase the number of energy channels. You can see from the top diagram, I guess, the different colors are the energy deposited into the different elements. So D0 is the first element in the stack, and then D1 and D2 are set further back in that instrument. And then we can use those to create a set of energy bins that then allow us to resolve the energy and indeed the species of the particles that come into the detector. And we're looking now at how far we want to push the number of energy channels so that we get the resolution that we need. We can do the same thing for protons. So this is then a calculation pushing through to the geometric factor that one gains, an energy-dependent geometric factor. For the LE sensor, you see the solution for the protons at the top, and then for the electrons at the bottom. And again, we're looking at the algorithms to maximize the number of channels that we would resolve, especially for the electrons in this sensor. You can do the same thing for HE, really to kind of just demonstrate the energy range that we have here in terms of resolution, and that we can successfully separate electrons and protons in the channels. And the instrument performance looks pretty good. There's a small fall off, as you see, in the geometric factor as you get to higher and higher energies. But of course, we can take account of that in terms of the way that the data is processed once it's collected. So just a few details about the microburst detector. If there are questions about this, I'm happy to answer them. But just to provide a brief overview, this is a scintillator design. So the basic concept is that the particles come into the sensor. It's ostensibly a 2-pi steradian sensor, and we'll have them mounted on opposite sides of the spacecraft, 2 sensors. And so the scintillator creates a photon response, goes into an MPPC, and then we read out the output from that after its amplification. So there's counts coming in here in the energy range around 100 keV to 4 MeV that will be covered by scintillators that they essentially screen the amount of flux that's coming in through an outer screen. I can talk about the details of that if people are interested, but this should give us 10 millisecond resolution of the microbursts across the range of energies that we need to advance microburst science. It's a redundant processor basis, fully redundant. So, for example, if one set of electronics dies, we'll have a separate set of processor electronics pathway that allow us to continue to operate. So that's the redundancy philosophy, at least for LE and HE. And broad layout, then the HE, as you see, is a back-to-back using the same stack. So it has views to the outside of the spacecraft, both in its left and right apertures. And then there's 2 separate LEs that mount with a common view direction. And then the current design right now is that the microburst detectors will sit kind of on top of LE, again, looking out with a 2-pi steradian view, 2 of them, in the context of the payload bay of the spacecraft. So data products, right now, as I mentioned already, these are the energy ranges for the LE and HE spectra, telescopic, and the number of energy channels is being traded at the moment to try to see how far we can push this. We're aware of interesting measurements recently showing the advantages from survey of high numbers of energy channels, and that's something that we're currently trading based on this design and comparing to the available bandwidth that we have to the ground. And then microburst detector, these 2 back-to-back 2-pi steradians, approximately 2-pi steradian, half omni detections at 10 milliseconds. So a brief overview of the X-ray imager. So the X-ray imager has the unenviable task, at least in spinning mode, of making a measurement of the X-rays that come back from the atmosphere to the satellite's location while it's spinning. So there's an element at which we need to be very careful in terms of how we characterize the spatial distributions on the spinning platform. Although, as I mentioned, we also have the capability to point. So we'll have a 3-axis pointing mode, which would be much more suitable for campaign-based uses of the X-ray imager as well. But it's designed to operate on the spinning platform. So its energy range is approximately 20 to 600 keV, and looking at the spatial distribution of the particles in the vicinity of the spacecraft. And mounted on 2 sides of the vehicle. And so then again, there'll be imaging towards the Earth from each of these detectors as the spacecraft spins. And Chris Cully could present many more details about this instrument. But here I got a kind of a quick view of the 2 pieces of this element. So the XRI team call this the A side and the B side. So the A side is based on the axis imager that's on the Apex CubeSat. So this is Bob Marshall's mission. I guess this slide says manifested launch for March 2024. I think that's, if I understand correctly, being delayed now till the summer at some point, although Bob could correct me. So this is well, I guess we'll see once Apex flies, but a high TRL instrument in terms of its design, due to fly. And so the baseline is to fly similar functionality design on the A side of XRI based on the Apex experience in partnership with Bob's team at the University of Colorado. And then the B side is a collimator design with good background rejection, focusing on the energy range rather than the spatial resolution. The TRL of this instrument is a little bit lower, although it's advancing quickly as Chris's team get this together in the lab. So both of these look like they're on track to be ready and tested for flight. But I say we're in a race with the solar cycle a little bit, but the trajectory looks really, really good. So I think this is a really interesting combination of the indirect measurement of the precipitation that we see from the X-ray populations with the in situ measurements at the location of the spacecraft. And I guess it's fair to say from instrumentation that flew on Barrel and the observations that we have, seems that the spatial distribution of precipitation is still very poorly characterized. So if we want to know the energy input into the atmosphere, we need to know not only what we see locally at the spacecraft, for example, in terms of the particles that sweep by the vehicle itself, but also what their distribution is locally around the spacecraft, because the overall energy that's deposited into the atmosphere must be a result of the combination of both of those aspects. And so the spatial distribution of this particle precipitation is extremely important as a scientific goal. And so X-ray imaging brings us that additional contribution. And then finally, the magnetometers. So this is David Milling's group, a number of people at the U of A working on this in physics. And so these are a combination of flux gate and search coil magnetometers. So the flux gate is targeted with verifying the direction of the background magnetic field, although we should have a very good indication of that based on attitude information from the spacecraft, models of the magnetic field in low Earth orbit, but also then to go after, I guess, the low period ULF waves that we can see, and especially EMIC waves that we'll be able to monitor from the FGM. And then the search coil magnetometer is set to try to focus on chorus and hiss, and has a frequency range that will encompass those transmissions that we'll see from ground-based transmitters. So we're interested in going after the studies of the transmitter-related precipitation, as well as the precipitation associated with naturally generated waves, obviously in particular chorus and hiss. So the mag payload is boom mounted, 2 FGMs, as mentioned earlier, and an SCM on the opposite side of the vehicle. These are the specifications on baseline compared to what we need. Needless to say that the design here should meet the specs that we need for the science. There's some heritage for this magnetometer, at least on the FGM side. So there's a long heritage, Barry Narod's work and others, the incarnation of these instrumentations for ground, that then with the EPOP mission was translated very successfully into measurements on orbit. A miniaturized version of the detector has flown on a number of CubeSats, so successfully on X-Alta 1, and was manifested on 3 other CubeSats that unfortunately didn't operate as planned. but we have an upcoming flight on the InspireSat-3 mission developed by an international consortium being coordinated by LASP, and then the instrument will then fly on radicals. So the InspireSat-3 project is developing. There's a series of these satellite platforms. Amal Chandran and his team at LASP in particular involved now in the integration of InspireSat-3 with an Indian bus. And so we will fly this magnetometer as a test flight on that platform, targeting integration and flat-sat testing this summer at LASP with a whole load of students actually from around the world. So that's exciting. Boom mounted, here's just some kind of comparison between the InspireSat-3 fluxgate and the ground-based sensor. So strong heritage from the ground being translated into space with, of course, the due upgrades in terms of radiation hardness and so on that are required for the space-based platform. Won't talk too much about this. The ring cores that make up that fluxgate sensor are made in-house in our facility at the University of Alberta. And so we've been able to test the cores and demonstrate that we can get to a really very low noise. So we have the capability to build an in-house fluxgate magnetometer instrument with very low noise and high sensitivity that easily meets the mission requirements that we have for the fluxgates. Search coil, I guess the technology is well understood, the mode of operation is well understood, and the heritage for this is ground-based sensors as well as a number of search coils that we've flown on balloon missions previously. The kind of eye candy on the right is the SCM instrument that flew on the EPEX balloon mission some years ago. And so the sensor well characterized and based on previous flight. So I guess I'm kind of coming towards the end of the slides here. Probably this is of less interest. So the bus is a University of Toronto spaceflight laboratory out of UTIUS. It's based on a Defiant XL bus, which is one that they have strong heritage in building. So I guess the key message here is the way that the spacecraft is set up is there's a payload bay that sits on top of a spacecraft bay. The spacecraft bay contains all of the relevant avionics, and then the payload bay contains the payload. There's a number of solar panels for keep alive, and the bus is designed with fold-out double-sided solar panels. And so there's some uncertainty about the MLT of orbit at this stage that we'll enter into. So the solar panel deployables can be deployed at a range of angles and optimized for different orbits. So this is showing you, I guess, just a little bit of the current baseline designs for the antennas, some of the instrumentation, where the solar panels lie, and some other details around the high-level aspects of the bus. And this is continuing to be worked, of course. And then the fields of view of the instrumentation look a bit like this. And so we have the basis within the payload bay to deploy the instruments with fields of view that have minimal impacts, especially from the deployable solar panels, which is very important. So a couple of final things to mention. The lowest TRL, I would argue, of the payload is actually this microburst detector, because that's something that we've just been working most recently in the lab. So very grateful to NASA Wallops Flight Facility and an upcoming opportunity for us to fly this microburst detector together with a single axis SCM enclosure on a student payload called Pepper-X. So that's due to fly in August of 2024 as part of the RockSat-X program this summer. So you can see some of the students involved in the team here. It's been a really nice opportunity to work with Wallops on this, and I'm very grateful to NASA and the Wallops team for taking our application, and for also congratulations to the student team for getting this into the rocket payload. So we'll have an opportunity to fly pieces of the lower TRL payload this summer on a sounding rocket from Wallops. So just coming back to kind of the overall science, I haven't talked too much about the science opportunity, but the combination of pitch angle resolved measurements and waves and X-rays. If you're interested in plasma waves and wave-particle interactions, I think this data set is going to be a really interesting one, combining the high temporal resolution data from the microbursts with X-ray flux information and the telescopic measurements of the pitch angle distributions is going to be really, really interesting. And so, of course, we're interested in the precipitation budget to the atmosphere for the climate connection. But the other end of that causal chain is a better representation of loss that would go from the radiation belts themselves. So there is an important aspect of radiation belt science here. And I think in order to better understand the dynamics of the belts, one needs to get the loss right. Otherwise, one has the possibility that you would have phantom radiation in models that should have been lost, but isn't. And then that phantom radiation would continue to be transported around in the radiation belt models to continue to provide, for example, apparent risks of radiation damage, which may not actually be there. So understanding both the acceleration and the loss side of this are very important for radiation belt specification modeling, risk modeling, and forecasting. So we look forward to advancing radiation belt science with this as well. So finally, just to touch on the climate element, this is a nice quote from Nessie Tissoy's paper in 2019 that's talking about the importance of this in terms of IPCC work, and a statement and quotes around the areas of uncertainty, which I think are still as valid as they were when this paper was written in 2019. The understanding we have, especially for medium energy electron precipitation, is quite poor, and we need a better characterization of that radiation and how it comes into the atmosphere in order to properly understand the magnitude of the effect. The models have the effect, but the parameterizations are still somewhat simplistic as compared to reality. So we have the opportunity to go and do some discovery science here with this, with impacts to better characterize the radiation, I guess the electron radiation impacts in these coupled climate models. So this is the goal. This is the same slide I had before, trying to parameterize this energetic particle element into this complex system of systems is an important and focused aspect of the science that we want to deliver with this mission. So I'll come back here to the summary. I think this is an exciting mission. You would say that you're the PI, but I welcome others to join us on this voyage. If you have science that you want to pursue with this, please get in touch. We'll be forming a broader science team for the mission as well. And so if you would like to be involved in that activity also, please get in touch. And I didn't mention it, but I will now. The data for this mission will be completely open. And so in my view, the more open the data, the more science returns. So we'll be embracing full open data with this mission. So anybody who wants to join us on this radical voyage of discovery is welcome to do so. And I'm happy to try to answer any questions that you might have. So thank you very much for your attention.
Great talk, Ian. Thank you for that. Just a quick follow-up for me. You mentioned the open data. Do you guys plan on having any sort of initial embargo for calibration like most missions? And do you guys know where the data will be available, or can you point people to somewhere where they can always find radicals?
So we don't have any radicals data yet, obviously. I mean, our plan right now is that there'll be a dedicated science data center for the project. So that would be the primary distribution hub for mission data. Whether we'll mirror that to other hubs is TBD at this moment in time. But we anticipate, a science data center with a public-facing distribution hub. To answer your question around the different levels of processing, so, I mean, we will make calibrated data available to the community as soon as it's ready. What that means is yet to be fully specified, but we don't anticipate any scientific embargo. And we're still thinking about whether there might be some value in releasing, how can I say, like level 0 data that's not gone through the full processing chain, in case people are interested in deltas and changes for perhaps some limited element of real-time data products, like kind of in I suppose the philosophy of providing a perhaps lower cadence data stream. So that's TBC right now, but our commitment will be to make scientifically valid data available to anybody who wants it as soon as we possibly can.
Awesome. So Doa has a question. She says, thank you for the talk. Are you looking at, or are you guys looking or interested or have been thinking about any conjunctions with Pfizer?
Generically, yes, but specifically, no, I suppose. I mean, I think Pfizer could be really interesting from the perspective of like incoherent scatter radar resolution of what's happening in the ionosphere as a result of precipitation of different energies is certainly of interest. So I could imagine really nice scientific conjunctions with overflights from the Pfizer facility and then trying to compare what we see in situ with the vehicles compared to what you're able to resolve with the ISR at Pfizer and elsewhere in terms of scientific coordination. So I think it's a really nice scientific opportunity. Beyond that kind of generalization, I haven't thought about it, but please talk to us about what may be of relevance in terms of science. I don't know if Pfizer needs to be in specific modes for high resolution and things like that, but that's the kind of science that we should be thinking about right now as we starting to kind of set in stone or start to set in stone the way that our data products will be defined. So we'd be happy to talk about this. That would be great.
Cool. And is the best place to stay up to date the mission website?
Yeah, it would be if it was live. So we're just about to tidy up. We have a mission website that's in preparation here, and so we'll put that out very shortly. It may actually be up, but just not advertised at this moment. So not sure if you sniff it, you'll find it. But we are about to tidy up and press live in terms of advertising a mission website. So it needs a little bit of polish, but it's nearly there. But that's probably the best place to go. And we'll be putting a mission paper out eventually on this too, of course, but it's a little bit early for that at this stage.
All right, excellent. Thank you again. So I think that concludes us for today. Quick note, there will be no seminar next week. I've made a mistake and double booked Ian and Harlan today. So we'll try and get Harlan to talk about helioswarm coming up into April or into the summer. But it does look like one more question came in, Ian, if you have time.
Sure.
Or a few questions. How does HEP distinguish between electrons and ions?
Okay, so I mean, so this is a DDX detector. So the energy deposition profile of the species is quite different. So you basically, in simple terms, you look at the energy that's deposited in different elements of the stack by the two species, and that allows you to get quite clean species resolution. I mean, the protons are quite well behaved, quite ballistic. So the getting nice clean ion energy channels and the deposition in the different elements of the stack from the ions is clean. The electrons are a little bit slipperier, so the energy deposition profiles are a bit broader, but allows you to resolve the species. I mean, I probably didn't emphasize this enough, actually, but the telescopes count every particle. So every particle that comes in creates a fingerprint of energy deposition into the elements of the stack. And then we use that to identify a particle that has come through the front of the detector and has the expected deposition along the line of sight. Even if a particle, let's say a very high energy particle, penetrates from the side and makes it through the side shielding, and we have a cutoff of, I think it's 60 or 80 MeV, so they'd have to be quite energetic. The chances of them putting a fingerprint into the stack that corresponds to a countable particle coming along the axis of the line of sight is extremely low. So that allows us to separate kind of a long axis from side penetration as well as between different species. And the resolution should be very clean, actually. We should be able to identify species and energy for each particle.
Excellent. And will those instruments be calibrated on the ground or with simulations?
Yeah, well, we have them all programmed in JAMP, but yeah, we'll calibrate them at beamlines on the ground in advance of flight.
Excellent. And his final question is, how does the X-ray detector reject bremsstrahlung from the body of the spacecraft? Or do you expect that to be an issue?
That's a good question. I mean, that can be an issue. Again, the X-ray imager needs, I think, shielding to try to avoid some of that? That's probably a question for Chris Cully or Bob Marshall. I mean, they're obviously aware of it, but that's something that does need to be taken care of. In the same way as I was just describing philosophically, that you want to try to make sure you're counting stuff that's coming from the atmosphere rather than that's being locally generated by interaction with the spacecraft. So I think the short answer is shielding. The longer answer is be careful, I think.
Excellent. All right. Thanks again, Ian. And I hope to see everyone. Our next seminar will be April 8th. Hope everyone has a good week and a good Easter holiday.
Thanks, Carl. Thanks, everyone.